Hi and welcome to UpSkul's Industry Readiness program for mechanical engineers. This is the first module of this course, which is dedicated to revising the core engineering concepts. We will start this module with the most boring subject, that is thermodynamics. Today we will cover the basic concepts of thermodynamics, Zeroth Law and thermometry, first law of thermodynamics, limitations to the first law, second law of thermodynamics, entropy, and third law, along with real-world applications, and prepare for MCQs and interview questions also. Before you start this program, I have something to tell you. In the next 5 days, we are going to complete 5 years since our inception. Since the last 5 years, I have been conducting this campus preparation program live on Zoom, just like every other coaching website. But this time we decided to make it different because pre-recorded lectures can be watched at your own pace, on your own schedule, without the constraint of having a fixed time for the live session. Engineering concepts can be hard and overwhelming, so you can pause, rewind, and replay complex concepts, ensuring that you fully understand everything, which is not possible in a live session. So make sure that you take adequate breaks between the different modules in every session. Issues like internet outages, audio lags, or software crashes are less likely to impact your experience. When you're preparing, every single minute of your life is important. In live lessons, time can be spent waiting for questions or technical issues. With pre-recorded lectures, you can get uninterrupted content delivery. So I hope you will make the most out of this course. Feel free to ask your doubts via email or Telegram group and our live session on Saturdays. Fill the Google form in the description to receive course notes, link to live Q&A sessions, job updates, MCQs and interview questions. And comment below, are you excited to crack interviews in the next 10 weeks? If yes, then let's proceed to the first section of this lecture, basic concepts of thermodynamics. So what is thermodynamics? Thermodynamics is the study of energy, heat and work in physical systems. It is fundamental in engineering fields like power generation, refrigeration and automotive design. A thermodynamic system is defined as the quantity of matter or a region of space which is selected for the study. The mass of a region outside the system is called surroundings, and the real or imaginary surfaces which separate the system and the surroundings is called boundary. Based on mass and energy transfer, the thermodynamic system is divided into 3 types: closed system, open system and isolated system. A system in which the transfer of energy but not mass can take place across the boundary is called a closed system. The mass inside the closed system will remain constant. For example, boiling of water in a closed vessel. Since the water is boiled in the closed vessel, the mass of water cannot escape the boundary of the system, but heat energy is continuously entering and leaving the boundary of the vessel. This is an example of closed system. Next, a system in which the transfer of both mass and energy takes place is called an open system. This system is also known as control volume. Boiling of water in an open vessel is an example of open system because the water and heat energy both enters and leaves the boundary of the vessel. Then a system in which the transfer of mass and energy cannot take place is called an isolated system, like tea present in a thermos flask, because in this the heat and mass of the tea cannot cross the boundary of the thermal flask. Therefore, it is an isolated system. Based on composition, there can be homogeneous and heterogeneous systems. A system which contains only one single phase is called a homogeneous system. For example, mixture of air and water vapor. They are both in gaseous form, right? Then a system which consists of more than one phase is called a heterogeneous system, like mixture of water and steam. They are both one substance but in different phases. And then we have the pure substance, a substance with homogeneous and invariable chemical composition, even though change of phase takes place, is called a pure substance. And the simple example of pure substance is water. Now let's look in detail of what is a control volume. Okay, a control volume is a system of fixed volume. This type of system is usually referred to an open system, where mass transfer can take place across a control volume and energy transfer can also occur in and out of the system. A control surface is the boundary of the control volume across which the transfer of both mass and energy can take place. Here, the mass of control volume may or may not be fixed. When the net influx of mass across the control system equals 0, then the mass of the system is fixed and vice versa. The identity of mass in a control volume always changes, unlike the case of a controlled mass system or a closed system. Most of the engineering devices in general represent an open system or control volume. For example, heat exchanger, where fluid enters and leaves the system continuously with the transfer of heat across the system boundary. Then there is pumps, where there is a continuous flow of fluid taking place through the system with a transfer of mechanical energy from the surroundings to the system. Now there are different viewpoints or approaches to a thermodynamic system. In macroscopic approach, a certain quantity of matter is considered without taking into account the events occurring at the molecular level. Whereas in microscopic viewpoint, the matter is considered to be comprised of a large number of molecules which randomly move in a chaotic fashion, and the effect of molecular motion is considered. In macroscopic viewpoint, the analysis is concerned with overall behavior of the system, whereas in microscopic viewpoint, the knowledge of the structure of matter is essential in analyzing the behavior of the system. The applications to macroscopic viewpoint is the study of classical thermodynamics. Okay, while microscopic approach is used in the study of statistical thermodynamics. Now you can look at the examples of macroscopic, where usually all the properties that we study in mechanical systems, pressure, temperature, etc., they are used to define a macroscopic system, and there are few properties that define a macroscopic approach. But in terms of a microscopic viewpoint, there are large number of variables like velocity, momentum, kinetic energy, and all these have to be described in a system. And these things cannot be measured very easily. So in terms of evaluation and calculation, macroscopic viewpoints consider the average value of the properties. So they can be calculated using simple mathematical formulas. Whereas in terms of microscopic viewpoint, the properties are to be defined for each molecule individually, and the number of molecules are very large. So it requires advanced statistical and mathematical methods to explain any change in this system. Now let's talk about thermodynamic equilibrium. A thermodynamic system is said to exist in a state of thermodynamic equilibrium when no change in the macroscopic property is registered, if the system is isolated from its surroundings. And an isolated system eventually reaches the state of thermodynamic equilibrium and can never spontaneously depart from it. Therefore, there can be no spontaneous change in the macroscopic property if the system exists in an equilibrium state. And a thermodynamic system will be in an equilibrium state if the system is in a state of mechanical equilibrium, chemical equilibrium, and thermal equilibrium. That means there is no change in the pressure, chemical change, or temperature change in the system. The thermodynamic state of a system is defined by specifying values of a set of measurable properties sufficient to determine all other properties. For fluid systems, typical properties are pressure, volume, and temperature. And for more complex systems, we may require specification of unusual properties, like the state of an electric battery requires the specification of the amount of electric charge it contains. Thermodynamic properties may be either extensive or intensive. The properties which are independent of the mass of the system are called intensive properties. For example, temperature, pressure, and density are intensive properties. But the properties which depend on the size or the extent of the system are called extensive properties. That is total mass, total volume, and total momentum of the system. These are very simple concepts. We are just going through them one by one. Okay. Next is thermodynamic process. When the system undergoes change from one thermodynamic state to a final state due to change in properties like temperature, pressure, volume, etc., the system is said to have undergone a thermodynamic process. There are various types of thermodynamic processes like isothermal, adiabatic process, isochoric process, or isobaric process, and reversible processes. Okay. Next is thermodynamic cycle. So it refers to any closed system that undergoes various changes due to temperature, pressure, and volume. However, its final and initial state are equal. So this cycle is important as it allows for a continuous process of moving piston seen in heat engines and expansion compression of the working fluid in refrigerators. For example, without the cyclical process, a car would not be able to continuously move when fuel is added, or a refrigerator would not be able to stay cold. Visually, any thermodynamic cycle will appear as a closed loop in a pressure volume diagram. Okay, for example, Otto cycle, diesel cycle, and Brayton cycle, etc. We will learn about them in the next session, that is on power cycles. Okay, now coming to reversibility. It is a characteristic of certain changes that can be reversed and the system stored to its initial stage without leaving any net effects in any of the systems involved. That means if there are changes in a system from initial state to a final state spontaneously or as a result of interactions with other systems, then those changes have to come back to their initial state without losing any of it. Okay, let's take an example of a single swing of a frictionless pendulum from one of its extreme positions to the another. Now what happens? The swing of the real pendulum is irreversible because a small amount of mechanical energy of the pendulum would be expended in performing work against frictional forces, and restoration of the pendulum to its exact starting position would require the supply of an equivalent amount of energy from a second system, such as a compressed spring in which the irreversible change of state would occur. Now, when a process is processing in such a way that the system will remain infinitesimally close with the equilibrium state at each time, such a process is called a quasistatic process or a quasi-equilibrium process. In simple words, we can say if a system is undergoing a thermodynamic process through succession of thermodynamic states and each state is equilibrium state, then the process will be termed as a quasistatic process. So let us consider a simple example for better understanding of a quasistatic process. If a person is coming down from the roof to the ground floor, he has two ways. Either he can come down with the help of a ladder or stairs, then it will be considered as a quasistatic process. But if he jumps from the roof to the ground floor, then it will not be called a quasistatic process. So how do we explain this in a thermodynamic fashion? Look at this diagram. The weight placed over the piston is just balancing the force which is exerted in the upward direction by the gas. If we remove this weight from the piston, then the system will have unbalanced forces and the piston will move in the upward direction due to the force acting over the piston in upward direction by the gas. Right? Now let's look at what is an irreversible process. It can also be called a natural process because all the processes occurring in nature are irreversible processes. So natural process occurs due to the finite gradient between the two states of the system. For instance, heat flow between two bodies occurs due to the temperature gradient between the two bodies. This actually is the natural flow of heat. Similarly, water flows from high level to low level. Current moves from high potential to low potential, right? So in the irreversible process, the initial state of the system and surroundings cannot be restored from the final state. During the irreversible process, the various states of the system on the path of change from initial to final are not in equilibrium with each other, and the entropy of the system increases decisively and it cannot be reduced back to its normal value. We will study about entropy in the next section. So this phenomena of the system undergoing an irreversible process is called irreversibility. But what causes this irreversibility? Okay. First is friction, and friction is invariably present in real systems. It causes irreversibility in the process as work done does not show an equivalent rise in the kinetic or potential energy of the system. So the fraction of energy wasted due to frictional efforts leads to deviation from the reversible states. Next is free expansion, and this refers to the expansion of unresisted type such as expansion in a vacuum. During this, the work interaction is zero, and without the expense of any work, it is not possible to restore initial states. Thus, free expansion is also irreversible. Next, irreversibility happens during heat transfer through a finite temperature difference. Now, heat temperature occurs only when there is a temperature difference between bodies undergoing heat transfer. During the heat transfer, if heat addition is carried out in a finite number of steps, then after every step, the new state shall be non-equilibrium state. Simply imagine a hot cup of coffee and a cold glass of water. Now the temperature difference between them is finite because the coffee is warmer than the water. So finite here means quantifiable. Okay. And this difference causes heat to flow from coffee to the water, a process that is not perfectly reversible. Then reversibilities are introduced due to lack of thermodynamic equilibrium during the process. Non-equilibrium may be due to mechanical inequilibrium, chemical inequilibrium, thermal inequilibrium, or electrical inequilibrium. And the irreversibility will be called as mechanical irreversibility, thermal irreversibility respectively. These factors we have discussed right now are also causing non-equilibrium during the process, and therefore they make the process irreversible. So what is this heat and work that we have been discussing for some time now? Heat is the energy in transition between the system and the surrounding by virtue of the difference in temperature. That is, heat is the energy transferred from one system to another solely by the reason of a temperature difference between the systems. Heat exists only as it crosses the boundary of the system, and the direction of heat transfer is from higher temperature to the lower temperature. For thermodynamic sign convention, heat transfer to a system is positive and heat transferred from the system as negative. That makes the calculation very easy when we are considering the system. Okay, now what is thermodynamic definition of work? Positive work is done by a system when the sole effect external to the system could be reduced to the rise of a weight. So work done by the system is positive and work done on the system is negative. And there can be different types of work interaction, like expansion and compression work, which we call as displacement work, PdV work. Okay. Then work of a reversible chemical cell, work in stretching of a liquid surface, work done on elastic solids, and work is also done during polarization and magnetization. Right. In mechanical systems, we mostly deal with the displacement work. Now what are point and path functions? Point function does not depend on the history of the system, it only depends on the state of the system. For example, temperature, pressure, density, mass, volume, enthalpy, entropy, internal energy, etc. Okay, but the path function depends on the history of the system, or we can say the path by which the system has arrived at a given state. For example, work and heat. The path function are not properties of the system, while point functions are the properties of the system. And the change in point function can be obtained from the initial and final values of the function, whereas path has to be defined in order to evaluate the path functions. For example, we have right now discussed different types of work, right? And when we want to calculate work done by a system, we have to define what kind of a work it is. If it is a displacement system, then we have to calculate the displacement, and based on that, we can calculate the work done by the system. Okay, so that was the end of section 1. Let us take a small quiz to make this session less boring. Question 1. Which of the following is a closed system? Air compressor, water bottle in a cap closed, boiling water in pot, or a jet engine? A closed system can exchange energy but not mass with the surroundings, right? So the sealed water bottle will always prevent mass transfer. So B is the right answer. Which of the following is an intensive property? Volume, mass, temperature, or energy? Now, intensive properties do not depend on the mass or size, right? And here, if you can see, except for the others, only temperature remains constant regardless of the system size. So the right answer is C, temperature. Question 3. Thermodynamic equilibrium means the system has 1. Equilibrium pressure throughout, no unbalanced forces, equilibrium temperature and no chemical potential gradients, or all of the above. So we discussed in equilibrium that a system will have thermodynamic equilibrium only when it has mechanical, thermal and chemical equilibrium simultaneously. So the answer is D, all of the above. Fourth, a process is called quasistatic if it occurs A. instantly, B. with high velocity, C. very slowly, D. with shock waves. So by definition, quasistatic process proceed infinitesimally slowly, maintaining internal equilibrium, right? So the correct answer is C, very slowly. Question 5. Which is not a cause of irreversibility? A. friction, B. sudden expansion, C. heat transfer through finite temperature difference, and D. isothermal compression. Now, isothermal compression can be reversed if it is performed very slowly, but the other options involve dissipative effects causing irreversibility. So the correct answer is D, isothermal compression. Question 6. Which of the following is a point function? A. work, B. heat, C. pressure, and D. none of the above. Point functions depend only on state, not path. So pressure is a state property, while work and heat are path functions. So here the correct answer will be C, pressure. These are some common interview questions which you can now very easily answer. Okay, so practice it well. Now moving on to the next section on Zeroth Law and thermometry. The Zeroth Law of thermodynamics says that if two systems are at the same time in thermal equilibrium with a third system, then they are in equilibrium with each other. This forms the basis of temperature measurement and applied in thermometers and temperature calibration. Now, when an object with a higher temperature comes in contact with an object of lower temperature, it will transfer heat to the lower temperature object, such that the objects will approach the same temperature and will maintain a single constant temperature in absence of other losses. That is how thermal equilibrium is attained. Now, thermometry is the science and practice of temperature measurement, and thermometry works on a very simple idea that when temperature changes, some physical property of material also changes in a known way. We choose a material that reacts predictably to heat. For example, mercury expanding in a glass tube, electrical resistance, and pressure of gas at a constant volume. And by measuring the change in that property, we can find the temperature. This measured value is then compared to a standard scale. Before understanding the different scales, first let's understand Zeroth Law with some common interview questions. 1. What is the Zeroth Law of thermodynamics and why is it important? Now, Zeroth Law simply says that if there are three objects A, B and C such that the temperature of A is equal to temperature of B and the temperature of B is equal to the temperature of C, then the temperature of A is equal to the temperature of C. That is, all three of them have the same temperature. This is important because it forms the basis of comparison of temperatures. How does the Zeroth Law define thermal equilibrium? The Zeroth Law defines thermal equilibrium as the state where two systems have the same temperature and no heat transfer occurs between them. Why was the Zeroth Law introduced later than the first and second law? This is also why it is called the Zeroth Law, because while the first and second laws were being developed, the concept of temperature and its role in determining thermal equilibrium was not clear. So the Zeroth Law, which essentially defines thermal equilibrium, was later recognized as the necessary foundation of understanding thermodynamics, and therefore it is called the Zeroth Law, because the first and second laws were already defined at that time. How does the Zeroth Law help in temperature measurement? Now, Zeroth Law allows us to define temperature as a measurable quantity because it establishes that systems in thermal equilibrium share a common temperature. And this is the basis for all temperature measurements, including the use of thermometers. Thermometers work by using temperature dependent property to indicate temperature, and Zeroth Law ensures that if the thermometer and the object being measured are in thermal equilibrium, the thermometer's reading accurately reflects the object's temperature. Can Zeroth Law be applied to all physical systems? Simply no. The Zeroth Law of thermodynamics is not directly applicable to all physical systems. It does not apply to systems that are not in thermal equilibrium or systems where heat transfer is not relevant. It does not address physical interactions like gravitational, electromagnetic or nuclear forces which may govern certain systems. Also, Zeroth Law is a foundational concept in thermodynamics, but it is not a comprehensive description of all physical systems. So what is a constant volume gas thermometer? It is a precise instrument used to measure temperature based on pressure changes on a fixed amount of gas kept at a constant volume. The key principle of constant volume gas thermometer is based on ideal gas law, which states that at a constant volume and gas quantity, pressure is directly proportional to temperature. And as the temperature increases, the pressure of the gas inside the sealed bulb also increases proportionally, since gas and volume are constant, right? So we can simply calculate the temperature by measuring the pressure. This is the formula where P0 and T0 are known reference pressure and temperatures. Now why is this important? Because it is highly accurate for defining temperature scales, especially in labs. It is used to calibrate all other thermometers, and it is very minimally affected by the nature of gas at low pressures. Now imagine inflating a tire at a constant size. If the tire is exposed to heat, the pressure rises. And that change in pressure tells us how hot the environment is, and this is the essence of how a constant volume gas thermometer works. Now there are three temperature scales used, that is Celsius, Fahrenheit and Kelvin. Celsius temperature scale, which is also called the centigrade temperature scale, is the simplest. It is based on the reading of 0 for freezing point of water and 100 for boiling point of water. Okay. Fahrenheit temperature scale is based on 32 for freezing point and reading of 212 for boiling point of water. This is the conversion formula. F is equal to 5 by 9 C plus 32. Kelvin temperature scale is the base unit of thermodynamic temperature measurement in the International System of Measurements. It is defined as 1 by 273.16, which is the triple point of water. The triple point is the equilibrium among the solid, liquid and gaseous phases of pure water. Now let's look at some common MCQ questions on Zeroth Law. Question 1. The Zeroth Law of thermodynamics helps define A. Heat transfer direction, internal theory, C. Temperature, D. Entropy. Answer is C. Temperature. Which of the following is the Practical application of the Zeroth Law of thermodynamics. Heat engines, refrigeration cycle, thermometer calibration, and first law of thermodynamics. So obviously thermometer calibration. Question 3. In a constant volume thermometer, what physical quantity is measured directly? A. Volume, B. Temperature, C. Pressure, D. Heat. So at a constant volume, pressure is directly proportional to the temperature. Therefore, pressure is measured to determine temperature. So the correct answer will be C. Pressure. Question 4. The temperature scale that assigns 0 degree to freezing point of water and 100 degree to boiling point is A. Kelvin, B. Fahrenheit, C. Celsius, D. Rankine. Correct answer is C. Which scale of temperature is absolute scale based on thermodynamic principles? This also we know, it is the Kelvin scale, because Kelvin is the SI unit of temperature and it starts from absolute zeros. The Kelvin scale is based on thermodynamic laws, not material properties. Which statement is true for constant volume gas thermometer at low pressure? A. Pressure remains constant regardless of temperature. B. Pressure is directly proportional to temperature. C. Volume changes with pressure. D. It measures entropy. B. Pressure is directly proportional to temperature because it is based on the ideal gas law. Question 7. What is the advantage of using constant volume gas thermometer? A. It is portable and inexpensive. B. It is highly accurate and independent on the type of gas. C. Works only at high pressures. And D. Can measure internal energy. Correct answer is B. Highly accurate and independent of the type of gas used. Because at low pressures, real gas behaves nearly ideally, making the thermometer accurate and less sensitive to gas type. Since this is too much to process, let's take a break. We will cover the rest of the sections in the next session.